Thanks for the invitation. I haven't given a seminar in Moscow ever before. I did visit once, but a long time ago, 1991, I believe. So this is mostly what I'm talking about is joint work with Misha. So the simplest version of the problem is how many regular graphs there are. I'm only going to talk about labeled regular graphs. R of G of n and d is the number of regular graphs of order n and degree d. And there's an example of one with order 8 and degree 3. So the number of regular graphs of order 8 and degree 3 is 19,355. Of course, you knew that. And you probably knew this one as well. The numbers get pretty big. We're interested in this talk in the asymptotic value as n is getting larger. For large sizes, there's only efficient exact formulas for degree at most 4. In principle, a formula can be made for any fixed d, but it becomes very hard very quickly, and I don't expect anything more than degree 5 to appear soon. We won't discuss those. What we will discuss is the approximate number as the number of vertices goes to infinity, and the degree is a function of the number of vertices. By complementation, we can assume that degrees at most n over n minus 1 over 2, and we'll ignore degree 0, and nd is always even. I won't mention that condition again. Degree 1 and 2 are simple student exercises. Degree 3 was solved in 1958 in the PhD thesis of Ron Reed. And then nothing happened for 20 years until in the late 70s, Bender and Canfield, and independently Nick Wormold solved it for arbitrary constant d. And the method they used, translated into the modern description, is one you've seen before, so I'll go through quite quickly. Everybody interested in random graphs has seen this 100 times. We want to make a 3 regular graph with 8 vertices, so we take 8 groups of 3 dots each, and then we take a random pairing of them, and then we collapse the groups down into vertices, and now we've got a 3 regular graph. However, we're only interested in simple graphs. I probably should have told you that at the beginning. And so this one doesn't count. It's got loops and double edges. So you try again and maybe you'll succeed this time. Okay, so now you've got a simple graph. And this model is the most important tool for counting and studying the properties of regular graphs of low degree. So to count regular graphs by this method, you say how many ways are there to make the pairing, which is that expression there. The result might be a simple graph, but the interesting thing is that every simple graph has exactly the same probability of occurring, and every simple graph, well, because every simple graph corresponds exactly to n factorial to the, sorry, d factorial to the n pairings, and therefore the number of regular graphs is equal to that expression times p of n and d, where p of n and d is a probability that a random pairing gives a simple graph, so probability that it doesn't make any loops or multiple edges. For very low degrees, you can estimate this probability using inclusion, exclusion, or method of moments. What happens is that you get an alternating series whose terms become much bigger than the value of the sum. And because you can only approximate the values of the terms, this method breaks down when the degree gets up to about square root log n. And Bolobach did that in 1980. To go further, you can use the method of switchings. And the method of switchings gives you, instead of an alternating series, it gives you a positive term series for the reciprocal of the probability. And I did that in 1985 up to little o n to the 1/3, and with Nick Wormald up to little o n to the 1/2 in 1991. All of these results, I've only talked about regular graphs, but they work also for non-regular degree sequences under some conditions. You can't have very large and very small at the same time, but you can have some reasonable variation in the degrees. The best result there is by Gao and Wormald, quite recent, where they did heavy-tailed degree sequences such as power law degree sequences, but still in the very sparse range, similar to the ranges that I've mentioned before. So most of the talk I'm going to be concerned with the other end of the scale, where the degree is very high. And in this range, the primary method is analytic. So the number of regular graphs can be written as a coefficient in a generating function. This is a product over n choose 2 terms. You have a 1 for a non-edge and xj, xk for an edge between vertex j and vertex k. And then when you expand that out, the powers of the variables monitor the degrees of the vertices. So you extract the coefficient of the term with all the variables to the power d, and that's the number of regular graphs of degree d. You can extract that coefficient using Cauchy's theorem, integrate each of the variables where you have to divide by the variable to the degree +1, the usual thing. Integrate each one around the contour enclosing the origin, divide by the right 2 pi I for each variable, and there's an answer. Okay, it's not a very good answer, but that's a start. So now we want to estimate the value of this integral. We'll let our contours be circles. I'm still doing just the regular case here. So xj, I'm going to write it as r times e to the I theta j. So r is the radius of the circle. And you're going to choose r to be square root of lambda on 1 minus lambda, where lambda is the density. This is the degree divided by n minus 1. It's the fraction between 0 and 1, specifying what fraction of the edges of the complete graph you have. So you make the change of variables, bring some junk outside the integral, this junk. Yes?
Sorry, can I ask you a quick question? So on the previous slide,
yes.
So can you maybe give some intuition or maybe explain it in a bit more detail, why the number of regular graphs is a coefficient in this generating function?
So think of expanding this product out completely and just collecting together the terms that are the same.
Yeah.
So if you have a particular graph, and for each j and k, you select 1 if jk is not an edge, then you select the xj, xk if it is an edge. Then in each term, the power of xj, or for example, is the number of edges incident with vertex j. Does that make sense?
Yeah.
Okay. So if you ignore this extraction here and you just expand that out, what you get is a sort of generating function for all graphs according to their degree sequence.
Yeah. Oh, okay.
And now we want just the regular one, so we extract the coefficient of the term, which has got every variable to the power d.
Okay, great. Thank you.
I think this originates with McMahon or someone like that, but he didn't go on from there. He wasn't interested in asymptotics. Okay, so now we're evaluating the thing by integrating around circles, and we've chosen particular radius for the circle. it won't work if you didn't choose that radius. And later on, I'll mention why this radius is necessary. So you've got some stuff that you took outside the integral, and then you've got integral of capital F. And now the integral is around from minus pi to pi for each of the variables, because you change variables to go around a circle like this. And the value of the function is this thing here. This is after you've taken out some terms and put them in front of the integral. Now, if you look at the nature of this thing here, in the bottom line, you've got exponential of an imaginary value. So that's got absolute value 1 all the time. On the top line, you can figure out that the absolute value is at most 1, and it's equal to 1 exactly when theta j plus theta k is a multiple of 2 pi, because that makes e to the I times theta j plus theta k equal to 1, which cancels out this 1, and then the value of the term is 1. So all the terms are at most 1 in absolute value, and in order to get all of them equal to 1, you have to have theta j plus theta k being a multiple of 2 pi. And so altogether, the maximum value of this function in absolute terms is achieved only at 2 points, namely when all the thetas are equal to 0 or when all the thetas are equal to pi. So now we'll take what we're planning to use is the fact that the value of the integral is concentrated at these 2 points. So we'll take a small cube that encloses, say, the point at 0. And inside that small cube, we'll expand the logarithm of the function, the logarithm of the integrand by Taylor series, so that the integrand becomes exponential of a series. And then by some means, which I'll discuss more a bit later, we estimate the value of the integral there. At the moment, I'm just giving you an overall outline of the method because I'm going to show how we refine it to get stronger results. Then outside this small box and a similar box enclosing the other point, which is equivalent to it, where all the variables are equal to pi, you can show that the integral of the absolute value is negligible. Now, both of these two steps, that's inside the box and outside the box, are not easy. They're quite complex. And part of our motivation was to try to make this stuff systematic so that it becomes almost like a cookbook style evaluation of the integral once you've figured out what the integrand is, rather than handling each case separately. So putting these two parts together with Nick Wormold in 1990, we got an asymptotic number of regular graphs, as long as the degree is at least n over log n. So it includes the case of degree being constant times n. And the method also works if it's not regular, but the degrees vary by an amount up to n to the 1/2 plus epsilon for small enough epsilon. So I've mentioned some calculations for low degree and for high degree. And when we did the low degree calculation in 1991, we discovered that we could write the answers in a form which was exactly the same for both the high range and the low range. And it also has an interesting interpretation, which I'll now consider. Let's think about degree sequence D1 up to Dn. So Di is the degree of vertex I, and the average degree is D. As before, the density is the average degree over n minus 1. That's a number between 0 and 1. And let's take an ordinary Edis-Rayne graph Gn lambda. So lambda becomes the edge probability. So first observation is that each graph that has the correct degrees, that's the degrees d1 up to dn, has exactly lambda times lambda times n choose to edges. So the probability that it occurs is lambda to the number of edges times 1 minus lambda to the number of non-edges. It's the same for all of these graphs, and call that P1. Next observation, if you look at a particular vertex, say vertex I, it's got n minus 1 possible neighbors. Each of those neighbors has probability lambda. So the number of neighbors is a binomial distribution, and the probability that vertex I has degree exactly di, as we want it to have, is this expression here. It's just a value from binomial distribution. Now we make a mistake and imagine that these events are independent. So we've got n different events, which are vertex I has degree di, and pretend that they're independent so that we can get the probability of all of those events at the same time by multiplying together the probabilities. Of course, this is not correct because these events are not independent. They're not independent because of the edge joining two vertices makes a positive correlation between the degree of those two vertices. But it's only a small positive correlation. You might guess that this is approximately a correct value. So call that P2. So now under this false assumption, the number of graphs with those degrees is this expression here. And I put the hat on it to be indicating this is the number under this false assumption. I call that the naive value. It's P2 divided by P1. The probability of all those events happening divided by the probability of each graph occurring. And that's the number of graphs. And so that's equal to this simple expression here. Now, why am I going through all of this? Well, in both the case of the sparse graphs and in the case of the dense graphs, the number of graphs asymptotically is equal to this expression here, the same expression both in the high range and the low range. We've got this square root 2 out here. We've got this naive number of graphs, and then we've got this correction factor, which is this exponential 1/4 minus some stuff. This gamma 2 is basically the variance of the degrees. Note that this gamma 2 is equal to 0 in the case of regular graphs, so this term here is 0, and you just get this magic constant square root 2 times e to the 1/4. And the conjecture says that the same constant works all the way from degree 1 up to degree n minus 2, which is somehow magic. We prove this in both the high and low range as long as the degrees don't vary too much from the average degree. So in between these two ranges, there's this huge gap. And this gap between the ranges foiled us for 26 years, but just in 2017, Anita Liebenau and Nick Wormald proved it using a method that involves a recurrence relation, but involving the number of graphs of different degrees. And they used this very effectively and managed to prove this conjecture by filling the gap between the high and the low range. Their theorem is actually like this. There's for some constant a greater than 0, the extended counting conjecture holds as long as you're greater than some power of log. This is the average degree, is greater than some power of log n and less than constant n. So it doesn't reach an arbitrary constant n, but it reaches some constant n, and this means that it overlaps the previous knowledge at both ends of the range, so the counting conjecture is now completely proved. All right, now, meanwhile, in 2013, Barvinok and Hartigan used an integral method to prove a theorem about the number of graphs with given degree sequence, but allowing a much greater variation of degrees. Instead of degrees varying only by about square root n, they allow even by a linear amount. So for example, their condition overall is a complex one. I won't mention it. But an example is that if every degree is in between 0.25 n and 0.74 n, then their method gives the asymptotic value. A downside is that their theorem requires the average degree to be a constant times n. It doesn't allow it to decrease. It doesn't allow it to be smaller than that. So the question is, can we allow smaller degrees and still allow a large variation from the mean? Now, let's look closer at the integral method. We have to estimate some integral of a complex function in high dimensional space. Usually if you counting graphs or something like that, or matrices, the number of dimensions is the size of the graph or the number of rows and columns in the matrix or whatever. And that's increasing as n increases. And we do it by approximating the integral inside some dominant regions and then bounding the absolute value of the integral of the absolute value in the other regions. There should be a little d in front of that theta just there. And this method has been used successfully before. There are more examples than this, but I ran out of space on the page, so I stopped typing. But the problem is that in these papers, if you look at them, you'll see about half a dozen different methods for evaluating the integrals using quite ad hoc methods that are different in each case. And also for the part where you have to estimate or bound the value of the integral outside the dominant region, that also varies a great deal between different papers. And we want to try to make this more systematic. I think we haven't yet done it for outside the dominant regions. We've made some steps in that direction, but we're still working on it. But inside the dominant region, we have now some nice theorems that cover all of the cases, all of these cases with one theorem for the integral inside the dominant region. I'm going to show you that theorem now. So a common feature of all these examples is that the integrand's close to the density of a Gaussian distribution. So this is the integrand you have to integrate inside some box. You have exponential of a quadratic form. Here, A is a real positive definite symmetric matrix. And f of theta is some other stuff, which is typically some terms of higher order. For example, in the case of regular graphs, you have terms which are like the sum of the cubes of the pairs of variables and the sum of the fourth powers of the pairs of variables. Multiplied by particular coefficients. And in the case of cubes, the coefficient is imaginary, which causes endless trouble. So now let x be the truncated Gaussian random variable whose density is proportional to just the quadratic part of this exponential of minus theta transpose a theta. So that's a quadratic form. If you multiply this by a suitable normalizing constant, you get a Gaussian variable. We're not integrating over an infinite range. We're integrating just over some finite box. So we have to truncate the variable at the edges of the box. But the box is chosen so that what we chop off is a very tiny part of the value of this variable. So if we let x be that particular random variable, then the integral we want is actually some normalizing constant times the expectation of e to the f of x. And that should be, no, little f. It's this little f that's in here. So take the first part as defining the measure, the random variable. And then you want to know what the effect of the second part is, the little f of theta. And it is c times expectation of e to the f of x. So what we want to estimate is things that look like that. The next thing that we realize, we didn't realize this immediately, but we came to it eventually, is that if you evaluating a multivariable integral by integrating over one component at a time, then what you're making is a martingale. So strictly speaking, you're making the martingale backwards. So I'm not going to write down a definition of martingale. You surely know it already. But roughly speaking, to make a martingale backwards, you take a random variable and then you average it a bit, and then you average it a bit more, and then you average it a bit more, and you keep doing that until you've averaged it completely and you have the expectation. And that's a martingale backwards. And that's exactly what happens if you perform the multivariable integration one variable at a time. So the expectations of exponentials of martingales have been studied before. For example, Hoeffding's famous lemma says that if you have a real martingale, so that the differences between the steps in the martingale lie in some real interval, then the expectation of the exponential of the martingale is in between the exponential of the expectation and the exponential of the expectation plus an extra factor. Now, Hoeffding proved this as a step towards his famous concentration theorem, but we don't want to take this extra step, at least not for this work. We want to actually stop here and use the thing that's in the middle and use this as our estimate of our integral. However, Hoeffding's lemma only works exactly like this for real martingales. Something like this is also true for complex martingales, but it's harder to state and much harder to prove. And usually it's not quite accurate enough. We have to go a bit further. And I'm not going to show you the most general theorem we proved about the expectation of the exponential of a complex martingale. By complex martingale, I just mean one where the variables have got complex values, nothing more than that. The problem in the proof is that the exponential function is not convex in the complex plane, even though it's convex in the real line. And that's why the proof is harder, essentially. So instead, I'll look at an important special case. So we have a bounded function from some product domain. Doesn't matter what these omega things are. So it's an n variable function from some product domain onto the complex numbers. And you define these two Lipschitz constants, first order and second order constants. And alpha sub k is how much the largest that the value of the function changes when you change the kth variable. And the delta sub jk is like the second difference, where you take alpha k and alpha j and how much can they differ from each other. So it's the original minus what happens when you vary j minus what happens when you vary k plus what happens when you vary both j and k. Now we make the alphas into a vector and we make the delta jk's into a matrix. And the theorem looks like this. X is a random variable with values in this product domain. And here it has to have independent components. For this particular theorem, it has independent components, even though our general theorem for martingales doesn't have this requirement. It's just more messy. For independent components, we have this, that the expectation of the exponential of f of x is equal to this stuff here. And you can see the first part of it going from here to here is, the first part is like in Hoeffding's theorem, the expectation, the exponential of the expectation. And then you have half the expectation of this square of the variation from the mean, you'd think this is the variance, but actually it's not. For complex random variables, this is called the pseudo variance. For defining the variance, they use the absolute value of the square of the absolute value, not the square. So you've got these two terms, and then the error term is this thing here, and we have in the top line here the variance of the imaginary part of f. So if it was a real valued function, the imaginary part, of course, is 0. So you'd have e to the 0, so that would go away, and you just have 1 plus L there. And the absolute value of L is bounded by this expression here. This was proved for real martingales by Gattoni with slightly different constants. Okay, so with this theorem, we applied it to the. It doesn't require a normal distribution like in most of our examples. It applies to any old random variable that's not too obscene, and even to things like sums rather than integrals. And of course, we made a theorem for the case of the normal distribution, and all of the examples I gave you on that big list of examples can be done just by applying that theorem. You just have to work out the values of things in the theorem and calculate the answer. So now I have to introduce cumulants, which you also have heard about. You probably know more than me. The theorem that I've just mentioned is good enough to do the integral inside the dominant region, all the examples I listed before, but it's not good enough to do regular graphs whose degree is lower than n over log n. And the reason, I'll go back. The reason is this thing here, the variance of the imaginary part of f. Remember I told you that in the case of regular graphs, this function f has some cubic term in it with imaginary coefficient. And as the degree of the graph comes down below n over log n, that cubic term starts to become very large. And this term in the error term here becomes so large that it completely wipes out everything else. And there's just no way to apply this theorem to get below n over log n. You even need even small constant n over log n doesn't work because it's up inside the exponential. So to go further, we need a new theorem. And let me talk about cumulants. We know what the second moments of a random variable are, just the expectation of powers of the variable minus its mean. And alternatively, we have a sequence of numbers called the cumulants, which can be defined in terms of the moments. And you can't see a pattern there, but the strict definition is this formal series that the expectation of e to the tz, which is equal to this. Here I'm just expanding out the exponential, and remember this is a formal expansion, is equal to exponential of this series here involving the cumulants. And just by equating powers of t, you get the formulas that I gave you before relating the cumulants and the central moments. Only K0 and K1 are affected if you shift the variable by a constant. So it doesn't really matter if you've got a mean 0 or not. So now let's let X be an n-dimensional vector, a random, well, it's an n-dimensional random variable, and the components are supposed to be independent. And f is an n-dimensional complex valued function. This word unpublished is in red for you, Misha. An unpublished theorem of Isaev gives a bound on the remainder when you apply this cumulant series. So that's the one I gave you here. And the thing that's on the left here looks like almost exactly what we want. We want something that looks just like that. And so we apply it, and there's our cumulant expansion. We were chopping off at some point rather than taking it to infinity, because in general it doesn't even converge. It's an asymptotic expansion. But chop it off at some point, you've got some remainder, and the theorem of Isaev gives a bound on the remainder under some conditions. And the bound depends on things like we've seen before, these first and second and third and so on, order Lipschitz constants. So delta 1 of f is the maximum it changes, the function changes when you change one variable, and then you've got this second order thing. It's just the same as before. And you have to calculate as many of these as you have terms in your cumulant expansion. And it looks like it's pretty awful, but actually it's not hard at all in general. If f is a nice analytic function, you can get bounds on these things just by taking derivatives of the function. So if you just take the first derivative, that gives you some bound on delta 1. And if you take the second derivative with respect to two different variables, that gives you bound on delta 2 and so on. And usually the differentiation becomes easier as you do more derivatives because variables disappear. So what do they have to do with our problem? We want to integrate something like e to the g of theta in a small region. Taylor expansion for g of theta looks something like this, a quadratic form plus some other stuff. And for the regular graphs, this other stuff has got cubic and higher terms. Now we find a matrix S that diagonalizes the quadratic form. S transpose AS is an identity. And we change variables. You know that any quadratic form becomes diagonal if you rotate it carefully into the direction of the eigenvectors. So you change variables like theta becomes S times phi. That's a scaling and rotation. And at the same time, you adjust the region of integration so that it's a cube aligned with the axes after the rotation. So you have to choose a little box that's not axis aligned to begin with, so that after you rotate it, it becomes axis aligned. And after you've done that, then the integral matches the theorem. We've got integral like this, where now the quadratic part is diagonal. So the random variable that corresponds to just e to the minus theta transpose theta is a lot of independent, it's a n-dimensional normal distribution with independent components. And then you apply the theorem to f of S times phi. And that's that. And you apply the theorem, it gives you an answer. Okay, go on. I said that. And what it gives you is an expression like this. There's some stuff that comes from normalizing constants. It involves the determinant of the quadratic form and some other stuff. And then you get some series. And you can get as much accuracy as you like. You choose your number p. And if you want accuracy order n to the minus p, you just have to take that many terms. And this works as long as the degree is at least some power of n. So now in any positive power of n will do. And that's the answer. This is just the integral inside the dominant region. You also have to bound the integral outside the dominant region. And in this case, it's much harder than usual because the integral of the absolute value is way too big. You have to take into account the fact that the integral oscillates a lot and cancels itself out almost completely, and use some nasty tricks in order to bound the value outside the dominant region, but it can be done. So when the average degree is about constant times n, we allow the degrees to vary by the same amount as Barvinock and Hartigan did. If the average degree is little o n, we allow the degrees to vary in between any two constants times the average degree. And in evaluating this expression, evaluating it for mixed degrees is pretty much hopeless, but you can evaluate it for regular graphs. And there's a standard procedure called Elise Theorem or Wick's theorem for finding the cumulants of functions of normal distributions. And you just apply that to evaluate these cumulants here. So the answer for regular graphs looks like this. There's an expansion. You can take any j you like, and then there's a polynomial of, so capital lambda is little lambda times 1 minus lambda. Remember, little lambda is the density. Pj is a polynomial of degree j, and there's the first 6 of them like that. The first few are easy to calculate because it gets harder and harder and harder. And the last one took about, I think, 10 hours of Maple to calculate. And these values I've got here are enough to give you the number of regular graphs when the degree is at least n to the 1 on 7, which well overlaps the earlier results on the sparse range. Some numerical values. Let's look at number of regular graphs of order 26 in degree 12, and we'll take more and more terms. And you can see the relative error starts off at just 2 digits correct, but ends up with 6 or 7 digits correct after you've taken as many terms as we calculated. Another thing we noticed is that our formula seems to work even when the degree is a constant, and it's just completely out of the question for our method to prove it. There's several places in the proof where we assumed the degree was growing as some constant power of n, and the proof just doesn't work for constant degree. But when we check the values against the actual values for constant degree, it's working there too. So that's something else to prove. So if this is true, then we can get the asymptotic number of regular graphs of constant degree to as many terms as we like, way past what can be done using the combinatorial discrete methods like switchings. Right, so we can generalize. So far, we've just considered all graphs with given degrees. Think of that as all subgraphs of the complete graph with a given degree sequence. And you ask, well, why complete graph? Take some other graph and ask for subgraphs of that, okay? So we'll take a fixed supergraph and count how many subgraphs of it have a given degree sequence. Well, as long as the supergraph is not too close to bipartite and it's got reasonable expansion properties, then we can do it by exactly the same method. And this allows us to do things like studying the probability of very large subgraphs in a random graph with given degrees. So if you want to know how many regular graphs of degree n over 2 contain a particular regular graph of degree n over 3, we can do it, that sort of thing. And I'm coming close to the end, but I can't resist mentioning the beta model. In the process of estimating nickel in the dominant region, you have to integrate each of the n variables around little circles. And if the graph is not regular, then you have to use a different radius for each variable. And let's say the radius for variable I is e to the beta I, and that's an arbitrary positive number. And what we want to, after we transform to the theta variables, is that the integrand is like a normal distribution plus some extra stuff. And that means we want to have zero derivatives at the origin. We want the normal distribution to be centered at the origin and not shifted away from the origin. And when you work out what that means, you get these equations have to be satisfied. Define lambda of jk to be e to the beta j plus beta k over 1 plus the same. You can see that's a number between 0 and 1. And the sum of theta jk over all k, except for j, gives you degree j. And you have to satisfy these equations, and these are called the beta equations. And we met them first because of our evaluation of the integral, but they come up independently of that, and I'll mention why they're interesting. If you make a random graph with degrees independently chosen so that jk is an edge with probability lambda jk, then what these beta equations say is that the expectation of the degree sequence is d1 up to dn. So the sum of the probabilities for one of the incident edges with vertex j is dj. And so that's the beta model of random graphs, has as its expected degree sequence the degree sequence we started with. And this has lots of nice properties. First property, the probability of any graph depends only on its degree sequence. And that's a characterization. In fact, it's not just the degree sequence you use to make the betas, but you can take any lot of betas you like and any degree sequence you like, then every graph with that degree sequence has the same probability. And the beta model is the only set of edge probabilities which has this property. The second thing, if you observe graphs, you assume you've got independent edges, and this is like how it's described in statistical journals. You observe some graphs, you're assuming that they're made from some model of independent edges, but you don't know what the probabilities of the edges are. But what you observe is the degrees of the vertices, and you have to estimate what the edge probabilities are from your observation of the degrees. Then these lambda jk things are the maximum likelihood estimators. Third thing, which is sort of equivalent to the second thing, Enoch noticed that if you make the matrix out of these lambda jk's, then the beta equations are exactly what you have to solve in order to get the highest entropy for that matrix. So the largest entropy of a symmetric matrix with zero diagonal, where all the row and column sums are equal to the given degrees, and all the entries except the diagonal, which is 0, are between 0 and 1. And you get, when you maximize the entropy, you get the same equation back. Chatterjee, Diaconis, and Sly showed that if you take if you have a normalized sequence of degree sequences, and that tends to a limit, this is in the graphon's sense, then the beta models and the uniform random graphs with those degrees tend to a common graph limit. Okay, Enoch and Hartigon showed that the beta model is close to a random graph with the given degrees in the following sense. You take some y, which is some set of vertex pairs, not necessarily edges, vertex pairs, and it has to be at least some fraction of all vertex pairs. Now you let x be the number of edges in a random graph with your given degree sequence that lie in y, and let x hat be the same number for a random graph in the beta model for those degrees. And then the probability that the actual number of edges in your random graph given degrees is this close to the expectation in the beta model is small, as long as this number here is large enough. So if you take a sufficiently large number of edge pairs to look at, then the number of edges you see there is quite close to the number of edges you see in the beta model random graph. Now, we didn't think this was very good because this number n to the 3 on 2 is too big. So we can significantly improve both of these. Forget D for a moment, and I think this is the last slide. So in the case of E, what we can put here instead of n to the 3 on 2 log n is something like the square root of the size of y. And moreover, instead of y having to be a constant fraction of all vertex pairs, we can choose any set of vertex pairs. Anything from all to nothing. And we get exponential bound there. So we can improve that considerably. And that's the end of the talk.
Yeah, thank you very much, Brandon, for a very interesting
Thank you,
talk.
Brandon.
Of course, I take questions.
Yeah, does anyone have questions?
I
So many, yeah, Misha has questions. Okay, Misha?
Misha's going to tell me all the things I said wrong.
No.
No?
I won't do that in public. But yeah, I know that's a bit hard to think at this time of the day, but maybe you have already answered in your head. So my first question is that all this hard work that we've done was basically to get a very precise formula for number of graphs, right? And we wanted to improve precisions. So number of graphs is given degrees. But what if we try only to estimate logarithm of the number of regular graphs and say get asymptotic of the logarithm of the number of regular graphs? So then we don't need to worry about all of this additional constant and stuff like that. Do you know a nice quick trick how to obtain or at least the rate of the growth of the logarithm of the number of regular graphs?
In the case of regular graphs of degree constant times n, the cubic and quartic terms in the integrand only change it by a constant. So if you can prove it, which is probably not too hard. In fact, I think Barvinok proved it. If you ignore those terms, then you get the answer within a constant, which is even better than getting the logarithm.
That's right, but you still do all the hard work.
If the degree is decreasing, I'm suspicious about getting the logarithm to any precision without doing a lot of hard work still. And the problem is that on the face of it, the function in the integrand, apart from the quadratic form, becomes highly oscillatory. And it looks like as you move towards the corners of the box, it just wipes out the quadratic form. And it's only somehow the magic of the cumulants that says that this doesn't actually happen when you evaluate the integral. You certainly can't do something as simple as just bounding the rest of the terms. This won't be anywhere near accurate enough. And I'm guessing a bit.
But is it
It
true
would be
that,
nice to have a, yeah.
Is it true that naive formula that you showed in the beginning of the talk with wrong naive assumption of independence, it always the right order of magnitude up to a constant, right?
Yes. Yes, there's the same constant. Here it is.
Yeah,
this
so-
term here is 0 for regular. So you just have square root 2 times e to the 1/4, the same constant all the way. And now that's proved because of Anita and Nick's theorem, Liebenau and Wormwold's theorem, where they've finished the proof between the low and the dense, the low and the higher degree.
All right.
But can you prove by some simple trick that this naive formula has got the correct logarithm? I don't know.
Maybe.
It might turn out to be a trivial question because, you know, these numbers are growing so fast. Let me give you another example. A problem I'd really love to solve, but I've got no idea how to solve it, is asymptotic number of Latin squares. An upper bound on the number of Latin squares is n factorial to the n, because each row is a permutation. And the actual answer is got the same, asymptotically, the same logarithm as that. Well, because there's a lower bound from somebody's permanent inequality that's got the same logarithm. So in that case, you can find the logarithm asymptotically, but it's really boring.
In the same vein, there is a question from Sergei Tarasov who asks for some open problems in this area.
Aha. Somewhere we have a list of problems.
There are not very much known for graphs, random graphs with, even for random regular graphs. For example, if you ask even super trivial questions about distribution of some statistics of random regular graphs, they're not known. For example, number of, or maximum number of common neighbors. It's not known, the distribution. So basically, we can do some estimates of the number, but if you want to find distributions of some statistics,
Yes.
this is not done.
So if you want information about subgraphs, like the number of subgraphs isomorphic to something, then we can give you the tools for finding any number of moments you like, the expectation of variance and so on. But you won't be able to find the distribution because these moments won't determine the distribution.
Okay.
So determining whether some things are log normal or normal distribution or something like that in the high degree regular case is an open problem. There's lots of problems that can be solved by methods like I've described that just haven't been done yet. For example, the bipartite case. I told you we can find information about the number of subgraphs of a given degree in a supergraph as long as the supergraph is not close to bipartite. But if the supergraph is exactly bipartite, then we can do it again. We just have a different integral. But we haven't done it. It would be still a lot of work, and we haven't finished writing up the complete graph case.
Actually, a precision from Sergei Tarasov, asking for some natural problems, so to say partition functions, especially recalling some giants from Australia.
Giants. Don't know any giants, Brandon.
we're talking about a person?
Well, I believe so. But so anyways, I guess he has sorry.
Exactly solvable models in statistic mechanics, pardon me, from Australia just.
Sorry, what's the question?
Book in the field.
Yeah.
5 years ago. Pardon me for the question.
I don't understand what the question is.
May I ask it orally, just by
Yes.
microphone? Yes. I mean, are there any exactly solvable models of statistic mechanics that are reduced and somehow related to counting regular graphs? And by giant, I mean one person who wrote the most profound book in the field 35 years ago.
Mm.
That was the
one on exactly solvable models.
Yes.
Rodney, somebody, what's his, Rodney, I know him. He's at my university.
Certainly.
He's retired now.
I know. Pardon for the question, and thanks for the answer.
I don't know the answer to the question. I do know that we have looked a bit at, Misha particularly wants to find the physics examples for his cumulant theorem, because there's quite a lot of estimates in physics that are done using expansion by cumulants, but they nearly always are non-rigorous. And so it's quite likely that his theorem can make rigorous some existing techniques, maybe invent others as well.
Sorry for interrupting. Adapt, it's possible to do exact. So all this method gives asymptotics, maybe even quite precise, but not exact. And some of the problems that could be solved with this method are actually hard in terms of complexity. So you can't hope to get exact expression on asymptotics.
So one thing that trying to find when we got okay, so you've got something like this e to the expectation. Expectation of exponential of y. You know, if you write change y into I times y, well, this lemma here doesn't work because it's only for real martingales. But expectation of e to the I times y is the characteristic function of y. So under fairly general conditions, it determines the distribution of y. Because of that, most likely the theorems we have that estimate the expectation of e to complex random variable can be used to estimate properties of random variables by means of estimating their characteristic functions. For example, things like central limit theorems. And this is something that we hardly started on yet. But it's a very likely application.
Thank you.
Now, I keep telling Misha that he should be working on this and publishing this theorem.
Yeah, that should be.
And were you the first who tried to prove theorems like this? I mean that such estimations for complex martingales, or there is some history of studying something like this Hoeffding lemma, but for complex case?
We didn't find any. Complex
Mhm.
martingales seem to be not used by almost anybody. Pretty much the whole literature. Well, there's some literature that's for very general things like, you know, random variables in Banach spaces and things like that. And some of that probably does apply for the complex case. But if you want to look for specifically complex martingales, you come up with hardly anything. This theorem I've got here, as I've mentioned, we found the paper by Catoni where he has a very similar theorem for the real random variable, but his method doesn't work in the complex case. When you're working in the real space, the fact that exponential function is convex allows you to use all sorts of inequalities that are simply not true in the complex case. So you have to use much more messy methods.
Okay, thank.
I have a combinatorial question. So
Oh, yeah?
this technique is useful for working with high degrees, right?
Yeah.
And then we have switching method for working with sparse degrees. So what would be the
Right.
best strategy if we at some point want to estimate the number of graphs such that half of the vertices have constant degree and half of the vertices have very dense degree? Is it possible to split this problem in two and you combine these two methods? Or, for example, is it true that the graph with such degrees behave basically like a bipartite graph plus a dense graph, like glued together?
Well, something that we haven't worked out at all yet, but a very simple case of that is counting bipartite graphs with given degrees, but where one side is much bigger than the other. So the big size has got low degrees and the small size has got high degrees. And how much different you can make the two sides is something that it's even hard to guess. When we did it before using, and what we can do with this theorem that I've got on the page here, and not the general cumulant theorem, what you can do with this only allows quite a small difference between the two sides of the bipartite graph. Each one can be like n to the epsilon times the other. That's about as much difference as you can make. So you can't have one side being the square of the other side. It just doesn't work. So to take it to an extreme, you could take one side of your bipartite graph to have constant degree and the other side to have dense, very dense, with very high degrees. I don't know how to do that.
Yeah, it seems like that's the first question that we need to answer.
It could be that some switching method does work.
Even
I don't know,
imagine half of the vertices of degree 1 plus. Shouldn't be that difficult.
well, that's easy because you can just take them off.
And how we adjust degrees of the rest?
Well, you take off vertex of degree 1 and it decreases by 1. You might have to do a sum over degrees of the graph after you remove the vertex of degree 1.
Okay. Yeah, so there are a bunch of questions related to this graphs with given degrees.
Yes.
It's partially addresses the question by Sergei Tarasov.
Yes. but what happens?
This technique is not limited just for graphs.
No, it's not limited just to graphs. Most of our examples have been graph type of things, but that might be more to do with the fact that we're interested in graphs. We're graph people. Of course, you can also do things like integer matrices and so on, and some designs like Kuperberg did some calculations with designs, but only in some fairly easy cases. It would be nice to expand the applications to a much wider field.
Am I right that your result works for when not all the degrees are equal? So when your graphs are not regular,
Yes.
then you should then you have this limitation for lower bound for degrees n to some power, some positive power. So if your minimum degree is smaller, then it doesn't work, or not. So you told that if your degrees are constants, it should work, but you don't know why. But if it is big constants,
you're quite right. We don't have the formula explicitly for the irregular case.
mm-hmm.
Even the formula, to get the formula explicitly rather than just in terms of cumulants, even for the regular case was difficult.
Mm-hmm.
To do it for the irregular case might be too hard. Where we could write some sort of expression, but computing it's quite difficult. Maybe we can evaluate it reasonably accurately by some simulation. I'm not sure. But the proof, even when the degree is low, the proof requires not too much variation between the maximum and minimum degree. Probably if they're within a constant, it'll be okay, but we didn't actually work out precisely what that is. There is some limit to the irregularity, which I'll try to explain. When you get an analytic expression like we're getting for the number of graphs at given degrees, it's a smooth function of the degree sequence. So if you change 1 degree by 2 or 2 degrees by 1, the value of the formula doesn't change very much for any reasonable formula that you can imagine writing down or obtaining by this method. However, if you take degree sequences that are too far away from regular, it's not true any longer that the number of graphs is a smooth function of the degrees. It even can go from a large number to 0 by just making a very small change, like changing 1 degree by 2 might take you from a large number of graphs to no graphs at all.
Mm-hmm.
And so it's hard to imagine what sort of a formula would actually have this behavior and work right in this extreme case. So for example, if you have a graph with half of the degrees have got, half of the vertices have got degree n over 4, and the other half of the got degrees 3n over 4, then you're right on the edge of degree sequences that don't exist.
Mm-hmm.
You see here above Enoch and Hardigan's result, which is the same as what we get in the case where the average degree is a constant times n. Their theorem works, for example, if the degrees are between 0.25n and 0.74n. And you will ask, well, why didn't they write 0.75 and have a much simpler statement? And the reason is that their theorem actually doesn't work if you write 0.75 there.
Yeah.
There are degree sequences in between 0.25 and 0.75 where the number of graphs is a very irregular function of the degrees.
Okay, I see. Thank you very much. Thank you again, Brandon, very much for this interesting talk. Thanks everyone for listening.
You're quite welcome.